Welcome back. Today we solve the classic microwave link budget problem. Here is the setup. We have a 1-mile microwave link operating at 1 gigahertz. The transmitter output power is 1 decibel milliwatt. Both the transmitting and receiving antenna gains are 25 decibel isotropic. The cabling loss at the transmitter and at the receiver is 2.2 decibels each. We have 5 questions. Part A. Which frequency band would you choose for the longest possible link? Part B. Which band for the highest information bandwidth? Part C. Find the received signal level, or RSL. Part D. If the receiver sensitivity threshold is -70 decibel milliwatt, find the fade margin. Part E. Which is the better design? Part C or Part D? Before we plug numbers in, let us understand our units. This problem mixes 3 closely related symbols, dB, dBm, and dBi. They look alike but mean different things. dB, decibel, is a ratio. It measures how one power compares to another on a logarithmic scale. The formula, value in dB equals 10 times log base 10 of the power ratio. Double your power, that is plus 3 dB. 10 times more, plus 10 dB. 100 times more, plus 20 dB. A cable loss of 2.2 dB means the cable absorbs about 40% of the incoming power. The rest gets through. dBm is an absolute power unit. It means dB above 1 milliwatt. So 0 dBm is exactly 1 milliwatt. Plus 10 dBm is 10 milliwatts. Plus 30 dBm is 1 watt. When we say the transmitter output is 1 dBm, we mean about 1.26 milliwatts of real power. dBi is antenna gain, specifically referenced to an isotropic radiator, a perfect sphere that radiates equally in every direction. 25 dBi means the antenna concentrates power about 300 times more than the isotropic reference in its main direction. It is still a dimensionless ratio expressed in dB. Now the trick that makes link budgets simple. Because logarithms turn multiplication into addition, every multiply or divide in the linear world becomes an add or subtract in the dB world. The unit algebra goes like this. Start with transmit power in dBm, an absolute unit. Subtract cable loss in dB. Absolute minus ratio stays absolute, still dBm. Add antenna gain in dBi. Absolute plus ratio stays absolute, still dBm. Subtract free space loss in dB, still dBm. Every term lines up so the final answer stays in dBm. That is why our RSL equation works. dBm minus dB plus dBi, minus dB plus dBi minus dB. All of it adds up to dBm. You can trust the arithmetic because the units always collapse the same way. One warning, never mix linear and dB units in the same expression. If you start with 10 milliwatts and try to subtract 96.6 decibels, stop. Stay in the dB world all the way through, then convert back to milliwatts at the very end only if you really need to. Before we crunch numbers, let us understand a link budget. Think of every element in the path as $1 in or $1 out of a bank account. The transmitter injects power. The cable at the transmitter side takes some away. The transmitting antenna adds directional gain. The free space path takes a huge amount. This is free space loss, FSL. The receiving antenna adds more gain. The receiving cable takes some more away. What is left is the received signal level at the receiver. The key insight is that free space loss grows with both distance and frequency. FSL in decibels equals 96.6 plus 20 log of distance in miles plus 20 log of frequency in gigahertz. Lower frequency, lower loss. Longer distance, higher loss. Parts A and B. These are band trade-off questions. For the longest possible link, we want the lowest free space loss. FSL scales with frequency, so we want the lowest frequency band. Among L-band, C-band, and millimeter wave, L-band wins. That is why long-range microwave links use the L-band. For the highest information bandwidth, we want the widest available spectrum. Higher frequency bands have more room for wide channels. Among our three, millimeter wave wins. It offers the widest contiguous spectrum for high-capacity links like 5G and beyond. Part C, Step 1. Compute the free space loss. FSL equals 96.6 plus 20 log of D plus 20 log of F. Substitute D equals 1 mile, F equals 1 gigahertz. The log of 1 is 0 in both terms, so 20 log of 1 plus 20 log of 1 equals 0. FSL equals 96.6 decibels. This is the loss the signal takes just from spreading out through space over 1 mile at 1 gigahertz. No obstacles, no atmosphere, just geometry. Part C, Step 2. Compute the received signal level. The link budget equation is RSL equals PO minus the transmit cable loss plus the transmit antenna gain minus the receive cable loss plus the receive antenna gain minus FSL. Plug in our numbers. PO is plus 1 decibel milliwatt, minus 2.2 decibels of cable loss, plus 25 decibel isotropic transmit gain, minus 2.2 decibels of cable loss on the receiver side, plus 25 decibel isotropic receive gain, minus 96.6 decibels of free space loss. Add it all up. 1 minus 2.2 plus 25 minus 2.2 plus 25 minus 96.6 equals negative 50 decibel milliwatt. That is the signal power arriving at the receiver. Part D. Compute the fade margin. Fade margin is simply how much extra signal you have above the receiver's minimum sensitivity. It equals RSL minus the sensitivity threshold. The receiver sensitivity threshold is given as negative 70 decibel milliwatt, so fade margin equals negative 50 minus negative 70 equals 20 decibels. This 20 decibels is your cushion against rain, atmospheric absorption, and other fading effects. Part E asks which is better. The answer: Part D is better because it has a 20 decibel margin. Part C had no margin. Any small fade would drop the signal below threshold. In microwave engineering, fade margin is essential for link reliability. The big picture. Every microwave link budget has the same shape. Start with transmit power, subtract cable loss, add antenna gain. Subtract free space loss. This is almost always the dominant term. Add receive antenna gain. Subtract receive cable loss. That gives you RSL. Then compare to receiver sensitivity. The difference is your fade margin. 3 takeaways. 1. FSL grows with distance and frequency. It dominates the link budget. 2. Antenna gain and low cable loss are the main design levers you control. 3. Always design with fade margin, at least 10 to 20 decibels, to handle real-world atmospheric effects. Good luck on your midterm.